Yeah, so I did not give the homework yet, so I think that it's almost the midterm season, so I will give the first one as the midterm, so maybe you will have at least 1 week to do the job. So basically, the idea of the homework and the midterm is that you have to write the full code and the full data analysis to get credits. So basically what you have to do is the same thing as, similar to quizzes, but the quizzes only requires just one answer. But for the midterm and the homework, you have to really make the figures and interpret the result verbally. Okay. So I think it's a good time to give the first homework or midterm because we are finishing the chapter 4 lab today, so you can do the basic analysis. We studied the linear regression in chapter 3 and the logistic regression and the linear and the quadratic discriminant analysis and the nearest neighborhood methods. So basically, you can analyze the most of the data in basic ways. So probably after finishing chapter 4 lab, you are capable of dealing with the entry-level statistical analysis in any area. So if someone in the medical school or biology department that ask you to do some data analysis, that probably that you can do.
Oh, is PCA a popular one as well?
Oh, PCA, yes, the PCA is also popular. Yeah, that's true. The principal component analysis is the unsupervised learning. So we will cover it in chapter 10. But yeah, actually, it's also covered in an earlier chapter. I forgot the chapter 7 or 8 when we study the principal component regression. Yes, so PCA is a method to lower the dimension of the data, so summarize the data. So if we have too many predictors, then sometimes it's hard to put all variables in the model. Even we have the model selection method. If we have too many variables, that we have trouble to choose variables. So PCA is used to summarize data before starting the regression type analysis. Yeah, so in short, we have suppose the 100 variables, then we summarize it into 10 variables first. Then after that, we do regression analysis or maybe some model selection. Okay, so now that we...
Can I ask a quick question going off the PCA? Would it be a common choice to do one-hot encoding, get tons and tons of columns, and then do PCA to try and reduce it back down?
Sorry, if we have tons of columns and the PCA.
Yeah, say I have a bunch of categorical variables. I'm using zip codes in a state or something, and then use PCA to try and reduce it back down. Is something like that a common practice?
Probably no. So the categorical variables, that's okay. So at first, think about the binary variables. It's totally fine to put the binary variables in PCA. So PCA can be applied for both continuous and binary variables. So categorical variables are mathematically equivalent to several binary variables. So you can put it also. So in that sense, the PCA is possible, but probably the the regression tree methods is more suitable for categorical data with many categories. Because it's not that efficient to apply the PCA for categorical variables with too many variables. Because suppose the zip code, we have, I don't know how many zip codes are there in the United States, but suppose
50,000.
50,000?
Correct. Yeah. This is I'm
Okay.
asking a real question related to my
Okay.
work.
I see. I see. I see. Yeah. So yeah. Yeah. So I think the regression tree type method is good. So basically, we categorize those zip code into several pieces. So that is probably the good way to go. So PCA, I'm not the expert of the PCA, so I don't exactly know how to do PCA for the too many variables. Probably that they will use the randomization, at least our algorithm. But the PCA is not obvious when the dimension is very high. I would say the 1,000 variables are fine, but more than that is not. So the zip code, if we have 15,000 zip codes, then we can code it into binary variables, but that means we have 15,000 variables, and that is not straightforward to deal with. So yeah, I think the regression tree, boosting, those kind of methods are probably good.
I appreciate the info and advice.
Yeah, and also the zip code, you have many prior information, right? So you can separate it by state, or you can, especially if you are doing prediction modeling, you can link many variables to zip code. At least the longitude and latitude of the zip code should be available online. I think the past students did that. And also, for example, the income, if socioeconomic variables are important, that you can connect the income with zip code, and that is much useful way to use the zip code, right? So if zip code itself, that is has very limited information, right? So you only see if the two lines are in the same zip code or different zip code. So that has very little information. So if you are doing the prediction, at least I suggest to connect the zip code with the maybe income data, crime data, and the longitude, the geographical data. Then you use those variables. Yeah, so that is probably a good way to go.
Super cool. Thank you very much.
Yep.
Sorry, Professor.
Yep.
I have a question about estimating μk for LDA and QDA for previous session. Regarding estimation μk, I thought that we estimate μk's, number of μk's, regardless our predictors. For example, if we have three main groups, horse, deer, and giraffe, then we will estimate 3 μk. But when with quizzes, I realized that we should estimate μk times our predictor, our x vector. Is that right?
Sorry, μk plus what?
For example,
yeah.
Yes, for example, when we have three main groups and also four x independent x for predictors, then we should estimate 12 μk, right? Three groups.
Yes, you're right. So if we have the three groups and the 4-dimensional, right? So yes, you're right. So we have the 12, the μk's, and plus we have the sigma, I mean the variance component, right? So we have to estimate. No, I don't exactly remember the question, but yes. So 4-dimensional case, the 3 categories, then we have 12, parameters in μk. That's true.
Okay, fine. Thank you.
Okay. Yeah, and QD, I think I remember that question. I think it was the correct answer is 42. I couldn't remember why that was for QDA.
22?
42, I think was the answer.
42. Yeah, you're right. I forgot the exact specification of the question, but okay. So let me see. Maybe I will share the screen.
I think it was quiz 3.
Quiz 3. Okay, thank you. Quiz 3.
Because I first put 12, but that one's wrong.
I think that is QDA. So we have the variance component. So this is the question. So can you see the screen? Yep. So quiz the 2, 10, 3. So suppose that there are 4 continuous predictors, so x1, x2, x3, x4, and the 4 categorical response variable, the whose values are the ABC. So we have the 12. And the QDA applied for this data set, how many parameters in total for mu k and sigma k. So mu k, as we discussed, we have 12 parameters. And the sigma k is basically 4x4 matrix. Right, 4x4 matrix. But the 4x4 matrix, but the that's symmetric matrix. The variance covariance matrix is always symmetric. So covariance of x1 and x2 is the same as covariance of x2 and x1. So that means that we have 4x4, but the it's symmetric. So we only have 10 free parameters. Right? So 4x4 is 16, but except for diagonal line, the lower triangle and upper triangle have the same information. So we have the in total the 6 parameters in, for example, lower triangle, and we have 4 parameters on diagonal part, right? So in total we have 10. So 10, and we have the 3 groups. So 10 times 3 is 30, right? So and 30 plus 12 is sorry. Yeah, 30 plus 12 is 42. So that should be 42. So 42. Yeah. Right. So the yeah. So the mu k, we have the 4 parameters each for 3 groups. So 4 times 3, 12, and sigma k, 10 parameters for each. For 3 groups. So you can see the 1, 1. We have the 4x4 matrix. So yeah. Yeah, so 2, 1 and 1, 2 are the same, right? So actually we only have the 10 free parameters, 4, 1, 4, 2, 4, 4, 3, 4, 4. Okay, so diagonal part are just independent. So I mean the only appears once, so 4 parameters, and upper triangle and the lower triangle are the same, 2, 1 and 1, 2. So sigma, this is sigma k. Sigma k is 4x4 matrix, but we have only the 6 parameters. 1, 4 and 4, 1 are the same. So 10 times 3. Then 30. So 30 plus 12. So 42 parameters. So just I would like you to see that there are so many parameters. So 4 predictors and 3 categories. That is pretty, small problem, but still we have 42 parameters. So sometimes we have the overfitting problem. If you have the 42 parameters in linear regression, probably you're concerned about the too many predictors in the model. Yep. Any other questions? Okay, so now we do chapter 4. Yeah, I think it's good to have more questions. It's good to have many questions because this is data science class, and the questions about data are especially maybe even better than listening to lecture. Okay, so chapter 4 lab. So sorry, I think I have to share the screen. I have too many windows, and I'm a little bit confused. Yeah. Okay. So I think that you are seeing screen. I think. Yep. So chapter 4 lab. So we have studied logistic regression and the LDA, QDA, and nearest neighborhood. So basically everything is for categorical, I mean, the classification problem. So in chapter 3, we do regression problem. So the predictor and response. The chapter 3 predictors are continuous. Predictors doesn't really matter, but the point is that the response is continuous. Chapter 4, the predictor is continuous. The response is the categorical. So most basic case is binary, for example, logistic regression. But we have the multinomial logistic regression for multi-categories, and the LDA, QDA, nearest neighborhood can be applied easily for multiple categories. Okay, so first, I set the width directly. Actually, we don't really use the files, so we don't really need it. And we use this library basically for data. So this introduction to statistical learning with R. So this textbook, the textbook's authors developed this package. And first, logistic regression. So think about the stock market data. So XT is the stock price on the on T's day. So stock price on day T. And stock price itself does not have much meaning, but the stock market return is important indicator. So basically, we think about the XT minus X sub T minus 1. So I would say this as the delta of XT. So this is stock market return. Yeah, so sometimes percentage return is more important, but the percentage return is sometimes hard to deal with because the 50% down, then after that 50% up, then it does not come to the original price, right? So 50% down, 50% up, that is actually, if the original price is 1, that becomes 0.5 and 0.75. So that is not convenient. So often that we use the log of XT minus the log of XT minus 1. In this way, basically this is almost the same as the growth rate in, for example, 0.01 if the stock price is up 1%, but also that this is symmetric. So one day the delta XT is 0.5, and on the next day the negative 0.5, then actually the XT returns to the original level. So often this is used. I don't know which measure was used here. So probably the log of XT minus log of XT minus 1, or yeah, so or some people just use the percent change. So just the XT or minus XT minus 1 over XT minus 1. So I don't know which one they used, but probably that they used this one. We assume. So basically percentage change, percent change. So stock market rate. Then, okay, so we have the data from 2001 to 2005. So probably the first line is maybe January 2nd, 2001, because the January 1st is the holiday. and January 3rd, January 4th, January 5th, and January 6th. Then stock market is open only for 5 days. Also some holidays. Today the stock market is closed because of the President's Day. Mostly university is open because we should have the same number of days: Mondays, Tuesdays, Wednesday, Thursday, Friday. So, but the stock market opens only 5 days a week without holidays. So maybe next one is January 9th. Then a year is fine. Then lag one. So this is the stock market return for 1 day before. So this is the return on probably December 31st. We assume that January 7th is Saturday in this setting. So Friday, so yeah. And the lag two means the return on December 30th, and the lag 3, December 29th, and so on. And this is, actually this is today's return. So this is the return on January 1st. Okay. And basically, but this is response. This is response part. So our objective is to estimate the direction of today's move by this lag 1, lag 2, lag 3, lag 4, lag 5. And also volume. So volume is actually observed at the same time as this price, but the volume, so this is the stock market volume. So today's volume is the 1.19 billion stocks, or I don't really know the unit, but the number of stocks traded. Okay, so this is the often popular way to represent the time series data for prediction purpose. So you can see that for in the next day, the lag 2 is the same as lag 1 on the previous day, because basically the 2 business days before January 3rd. So that is the same as 1 business day before January 2nd. So basically we have the same numbers here, and we have same numbers here. So basically, we have the same numbers again and again, but in this way that we can easily set up the predictors. So we have the predictor x1, x2, x3, x4, x5, maybe x6, and then in our case, y is basically this one. So direction of today's move. Do you have any questions about the data structure? So if you do final project, if you deal with time series, the data for final project, this is one useful way to do some prediction. Okay, so now that we want to regress this y on other variables x1 to x6. And for logistic regression, we use the GLM function. So linear regression, we use LM, but this is more generalized version. And the GLM function, without any option, they do just linear regression. GLM is equal to LM. I mean, GLM with no option. Default. This is LM. But for logistic regression, if we specify family is equal to binomial, then this becomes logistic regression. I mean, the binary regression, and the binary regression without any option, that is the logistic regression. So we can also specify some other link function. If we do probit regression, then we can do that. But binomial, the default is logistic regression. And the other things are almost the same. So
sorry,
yeah.
Professor.
Yeah.
About response variable, I think it should be 1, 0, and something like that, because
Yeah. Yes.
R don't recognize up and down as yes.
Yeah, so I think that we have to code it in some way. So basically the up, down, so this is a factor variable. And probably that I'll recognize this as 1, 2, maybe, I don't know, but this is a factor variable. So factor variable means that this looks like letters, but I'll recognize that these values are the same, and these values maybe only one, but the down and up are different, but only 2 categories that are recognized. And as long as we have the factor variable with only 2 values, then R can do the logistic regression. That's right. So if we have the character vector, then we have to make it into the factor vector before doing logistic regression. Or if we have, yeah.
Thanks.
Yeah, sure. Yeah, that's a good question. Yeah, so yeah, I think the most difficult part in R is, I mean, most confusing part is the class of variables. It looks like the character vectors, but sometimes factor vectors. It depends on the R version, but sometimes R automatically change the character vectors into factor vectors when you create the data frame. So within data frame, usually we do data analysis. So factor variable is more convenient than character variable. So sometimes it's confusing, but I think that these days you can just include character vector in data frame. In the past, I think we have to use some special option to include character vectors in data frame in our language. Yeah, so this S market data, this is a data frame. Okay, and the data, you can specify data. And as long as you can specify data, you can use local variables. So this lag1, lag2, these variables are only defined within this data frame. But since we have specified data, we can use these names without attaching this S market data. And this is the output. You can see that we have estimate. So this is the beta I hat, and this is standard error of beta I hat, and a Z value. So this is the beta I hat over standard error of beta I hat. So this is approximately normal, 0, 1. And this is the probability. For example, this is negative 0.523. So that means this is the normal 0, 1 density. Then if we think about negative 0.523 and a positive 0.52, then this area is 0.6. So if this area is very small, then we can say that this value is significantly different from 0. So this is p-value. So it's a p-value. Yeah, so we have the lag1, lag2, lag3, lag4, lag5 volume. So we have 6 variables. And you can see Z values and P values. So even though these are not significant, you can notice that these are relatively larger. So lag1, maybe also this one. So this means that at first, the lag1 and lag2. So in the previous 2 business days, stock is down, stock market is down. Then today, on that day, the stock market is more likely to go up, right? So the different directions. We have negative sign, so go up. Oh, it really depends on the which up and down, how up and down are defined. But here, I think the down is 0 and up is 1, basically because the up is alphabetically later than down. You can change the those definition by using, I think, the levels function. Yeah, and that's it. And yeah, and the volume, we have positive the coefficient. So larger transaction volume means they're more likely to go up. So this is slightly different from prediction because the volume is observed at the same time as the today's price. So I don't know, it's forecasting or not, but at least it explains the today's price movement. Yeah, and the null deviance. So these statistics, I think we haven't covered in detail, but basically we can test whether or not we can test whether or not the model is sufficient. So basically, yeah, so we can do testing and yeah, so residual deviance. So basically, this statistic follows chi-square distribution with residual, the degrees of freedom 1,243. So, and the chi-square distribution with degrees of freedom k has expectation k. So that means that this number is much larger than this number, then residual is too large. So, but anyway, so we cover this in the 6840. And AIC, this is prediction performance. The smaller is better. But you cannot compare this between different data set, different data set. Sometimes AIC is not comparable between different models because the different packages have slightly different definition of AIC. And the table of direction. So this is just the summary statistic. The stock market is up for 6. Yeah, so in 602 days, the stock market is down, and 648 days, the stock market is up. And the coding is here. So if you type contrast, then you can see the down is interpreted as 0 and up is interpreted as 1. So that's why the logistic regression works. And the fitted value is basically expectation is an exponential of the beta transposed x over 1 plus exponential of beta transposed x, or you can say 1 over 1 plus e to the power negative beta transposed x. So here beta is the vector of coefficients. So we have the 6 predictors. So we have the 6 components in beta, and x is predictors, so 6-dimensional vector. So this is the predicted probability. So this is the fitted value. So we can calculate for this fitted value for each observation. So this is the first observation to 6 observations. So first one predicts it explains the probability that the stock market is up on the January 2nd in 2001. This is the January 3rd, January 4th, January 5th, 6th, and the January 9th, and so on. So this is basically 5 years of data. So 5 years of data. So that's the probability. So on January 2nd, on the first day, the stock market is predicted as has predicted to have the positive return with 50.7% probability. So slightly higher than 50%. And the next day, 48%. Next day, 48%. Then the 51.5%. So probably this is the best day. And you can see that these are more than 0.5. So stock market is more likely to go up. And another way to put it is predict variable, predict function by using predict function. This is a little more convenient because we can specify several options. But here, basically, we do exactly the same thing. So these numbers are the same as the previous output. Coefficients we have already seen in the previous table. So these are coefficients of the variable. So beta naught hat, beta 1 hat, up to beta 6 hat. You can see these numbers here.
My confusion on using the lag, does that mean you can only predict 1 day out?
Yes.
Or do you use your predictions to fill in the lag for the future predictions?
So only the 1 day future prediction. So if we have data up to today, that we can predict only the tomorrow's price. We cannot predict the price the 2 days later. So I mean, today is, for example, the 15th. So we can now predict only the direction for February 16th. We cannot predict 17th.
Okay, thank you.
Yep.
Sorry, Professor. I have two questions. First,
sure.
Can we see row square or adjusted row square or log likelihood function in R?
No, we cannot define that. So remember that the adjusted R square and R square.
Row square.
Okay, so yeah, R square maybe. So 1 minus the residual sum of square over total sum of square, right? So, but the sum of square cannot be defined for logistic regression. So we have the modified version, actually, we cover it in 6840, but we cannot define adjusted R square in logistic regression.
I know, I just asked about row square.
Row square.
Yes, row square and adjusted row square. I think that we have row square for this kind of categorical modeling, yes?
Sorry, what lowest square?
Yes, row square and adjusted row square.
So what do you mean row? Row is the correlation?
Yes, row is something like R square for linear regression that we have in multinomial regression or in binomial regression. It's some kind index of goodness of fit, or I don't know. It's something like R square for regression, for linear regression.
So basically, in terms of the measure for the fit, such as R square or rho square, the linear regression and logistic regression have totally different stories. So we can define some quantities which is kind of similar to R square or rho square, but I believe that we don't really have the exact correspondence between linear and logistic regression.
Yes, that's true. And one other question, I didn't understand the predict function for predict the tomorrow stock market. I didn't understand this line of thought.
So this is actually, yes. So this is actually the fitted value. So okay, so what we did is that we have the data from, okay, so we have the, okay, so yeah. Suppose our data set have n observations and that we have the response yn. So we only calculated the y1 hat to yn hat. So we are not really predicting the data in that sense. But if you plug in the new observations, we have not plugged in new observations. But if in the logistic regression model, if you plug in the new observations, for example, xn plus 1, then we can get yn plus 1 hat, even if we haven't observed yn plus 1. So in that sense, we can do the prediction. So for now, we only calculated these fitted values. So it's not really we are predicting the future. So we are checking our model performance for the past data. So it's not really predicting in that sense. But at least we have already estimated the model. We have already estimated model. So if we observe new observation, new predictors xn plus 1, then we can predict yn plus 1 hat. So that is what I wanted to say.
Thank you.
Sure. So yeah, so here that so we use the two methods to calculate fitted value, the y1 hat or yn hat. So actually this is the probability that the y1 is equal to 1. So maybe, yeah, I would say that this is probability of y1 is equal to 1, right? And how to calculate it? So of course, in terms of coding, this or this can do the job. But what's the theory behind it? Then that is here. So at first, we have to calculate the beta naught hat times 1 plus beta 1 hat times the first component, if ith observation I1 up to beta 6 hat x I6. Okay. This is the first component of ith observation to 6th component of ith observation. So this can be done by taking the summation of the product of coefficient. Right? So this is the coefficient vector. So this is the predictor and 1. 1 is for intercept. So if you multiply and take summation, then we can get the linear combination. Right? So we can calculate this value. Then we put the logistic function to calculate fitted probability. Then we get the same answer. So actually the fitted function or predict function basically do this calculation. Okay, so now we have calculated the probability, the predicted probability to go up for each day. So we want to calculate predicted value. So our predicted value is, so we want to say that our predicted value is either up or down. So for that purpose, that we set the threshold at 50%. If fitted value is more than 50%, that we regard that as up. If less than 50%, that we regard that prediction as down. Then we get this vector. So true is up and the false is down. True is predicted up and this is predicted down. Then we can make a contingency table or confusion matrix. So this is prediction and this is truth. Prediction. So basically, these observations are predicted correctly. So predicted up and the direction is up. And the off diagonal part, so these are mistakes. So these are error. So how many percentage of error? We can calculate it by just extracting the data set, the data here. So this is error and this is so this is total number. So error rate is 47.8%. So of course, stock market is hard to predict. So error rate of 78%, 70 47.8%. That's a kind of reasonable. But remember that we are just using this data set to fit the model. Then we just calculated these fitted values. So it's a kind of the situation that we know the answer, but just we summarize the data into the parameters. I mean the parameters in the logistic regression, and we calculate this. So it's not really a prediction. So we just fit the data and check if the fit is good. So we are kind of we know the answer and we are doing prediction. So it's not really a fair prediction, but still the error rate is 47.8%. So in terms of prediction, we have to have the test data. So we have the training data and the test data. For example, we have 1,000 days of training data, and we test this model performance with the other 250 observations. So the situation is that we observe the predictors for x1 to x1000 and the y1 to y1000. Sorry, 1000. And using this data set that we estimate the model, then using x1001 to x1200 500 to predict these values, y 1001 hat to y 1250 hat. So we want to set the test set and the training set and the test set, and we want to check the performance of this test data set. So to do that, we separate the training set into two parts. So sorry, the data set, original data set into two parts. The training set is year 2001 to 2004, and the test data set is 2005. So usually time series that we have to, we want to do in this way. So if independent observations, such as 100 patients, just randomly split the data set into two. But the time series, the time structure is important, and the doing prediction for later years is more important. So it does not make much sense if we use 2005 data to predict 2004 data. So that does not practically make sense. So the usually test set is the later period than the training set. So the training set, so we just set the year is less than 2005. So that is basically a training set. So we have the year column. So the first 1,000 observations are in the year 2001 to 2004. And the remaining 250 observations are in year 2005. We have 5 business days and approximately 50 weeks per year. So that's why we have 250 observations. Okay, and this is the test set, S market 2000. This is test set. Because this is not trained, so this exclamation mark is not. Yeah, so this is test set. So basically, the train is an indicator variable, and not train means the test set. So basically the first 1,000 observations that is false, and the remaining 250 observations true. So this is 1 to 1,000, and the 1,001 to 1,250. So if this vector we put here, then this we can extract the test set. And we didn't specify columns, so that means that we get all columns in original S market data. Okay, so now that we have so now that we can fit the logistic regression with only this training set. So basically the same code, but the subset train is added. Then this is the estimation result. Actually, it's good because these coefficients are similar to the previous one. I think the lag one has slightly larger coefficient in the past, in the previous regression result. Maybe this coefficient was negative 1.5 something, 1.4 maybe, 1.45 and negative 0.84. So it's a kind of robust. But because the 80% of the data set observations are extracted from the original data set, so probably that's reasonable. But the volume, it's slightly different. The direction is actually opposite. But it's not uncommon because anyway, p-values are not significant. Yep. Oh, maybe the number of iterations. So logistic regression is numerical procedure. So it outputs how many iterations were done. Then we can predict the performance of the data. You can see that with this way that we can predict the performance for 2005 data. So this is the new data, basically. You can also write new data is equal to smarkets.2005. So basically, we use the estimated model. So this is trained from 2001 to 2004 data, but we now plug in numbers for the new data. So in this way, that we can do prediction. Then we set 0.5 hours threshold and make the same table. And actually, it looks, it does not look good because the error rate is 97 plus 34 over the total. Total is what? The 121, 131, maybe 252. 252. So actually, it's not really good. Error rate is 52%. So any binary regression analysis, if error rate is more than 50%, it does not make any sense. So that means the stock market is not predictable with this analysis. Okay, and another way to do prediction for the new data, we want to also add some hypothetical observations. Then we can do this way. So we define new observation as 0 return in the past 5 days, and the volume is 1.42. Probably 1.42 is the mean volume of the data. So if stock market does not change for the last 5 days, what's the predicted probability to go up in the next day? That is actually the 51.65%. So this can be done with this code. So basic idea is that we have to prepare exactly the same structure as the training set. So if training set have the x1, x2, x3, and we have 100 observations. So if this is training, the test set, it should have exactly the same name, x1, x2, x3. Of course, we have different observations, so maybe only 1 to 10 and the new data set, but it should have exactly the same. So if x1 is categorical in training set, x1 also has to be categorical, and the name should be the same. Everything should be the same. Maybe only the exception is that if some columns are not used, for example, x4 is not used, it may not have to be included in the test set. But except for that, everything should be exactly the same shape. Everything should have exactly the same shape. So that's why we define the lag1, lag2, lag3, lag4, lag5, and the volume, and create the data frame with these variables. Then, yeah, so this basically removes original variables. So basically, we created this, but after that, we created the new data frame. So log1 is within the new, and also we have the global log1. So we delete this. So remove these objects. Then we can do prediction. So training and test exactly should have the same shape. Exactly the same structure. So this is useful, important fact if you do some projects. Yeah, so only the exception is if some columns are not used, then you can ignore it. So originally, S market data include the year column, but here we don't have year column because year wasn't used for the prediction. So that's why that we don't need it. And the next second observation is what happens if the past the 5 business days return is 0.5%, positive 0.1% each. So stock market is go up 0.1% for 5 days in straight, then what happens in the next day? Actually, the stock market will go up again with 51.4% probability. And another case is just 0 return for 4 days, and after that, the negative 1% return on the next day. So that is large negative return. Then next day, the 53.5% positive return. So remember that the log1 coefficient is negative. So if stock market goes down in the next day, on the next day, the stock market is likely to go up. Yeah, that was especially true for the old data when information is not perfect. So people see the stock market price in the newspaper. Now everyone look at the data on the internet, but yeah. Does anyone look stock price on the newspaper these days? Probably no one do that, right? So I don't even know the Wall Street Journal have the stock price on the newspaper. I mean, individual ones. Do you know?
I believe it's just the Dow.
Just Dow, okay. Yeah. So that's true. So I think that the Japanese newspapers, they still have the stock price, every stock price on the newspaper. So that's very old fashioned. Maybe 80 years old investors still look at it. Yep. Yeah. Okay. So this is. Yep. Go ahead.
Can we plot ROC curve to see that our model is good enough or not?
ROC curve.
Yes.
ROC curve, you have to use the different package, I believe. So as far as I know, the ROC package and ROC function. So the basic idea is that the ROC curve needs only the 2 things. So the one thing is predicted value. So that is this vector, and also the original. Sorry, this is new data set. So ROC curve is for existing data. So basically, we need the 2 things. So basically, we need the response and the predicted, right? So basically, the answer is that you have to put the predicted fitted value and the actual. So you need 2 vectors, and you put 2 vectors in this function, then you can do ROC. You can make ROC curve. So basically, you have to use another package.
Thank you, Professor.
Yep. Yeah, I think today there's so many good questions. Any questions for logistic regression? Okay, so now that we will go on to the linear discriminant analysis. Logistic regression, GLM function is in the default R package. I don't know which package there is it. You can just search for it in our language, help of GLM. And actually the stats package, so the GLM in stats is in stats package, and the stats package is loaded as default, so you don't really have to attach. But for LDA, linear discriminant analysis, that we have to use the mass package. So this is pretty popular package, probably one of the most popular one, but still you have to load package first. Then you can use this LDA function. Then the format is the same. So just for illustration purpose, I put only 2 variables, but you can put many more variables, lag plus lag 3, plus lag 4, and volume, and so on. The format is exactly the same, but the output is of course different. And this is prior probabilities. So this is basically the summary statistics. So 49.2% of observations are down and 50.8% up. And the group means, so this one. So this is the vector of mu1 hat, and this is mu2 hat. We have 2 predictors, so 2-dimensional vector. Then coefficient of linear discriminant linear discriminants. So that means that this negative 0.64 times lag 1 plus negative 0.51 times lag 2. So this is the best indicator to divide 2 groups. So this linear combination is a linear discriminant function. So that means this separates 2 groups the best. And if we use this function, the actually the distribution of this statistic is this for the days of stock market down, and this is the descriptive statistic of this variable for days of stock market is up. You can see that the stock market prediction is hard, so these 2 distributions are similar, but you can see the center is probably around here and probably around here. So slight difference, right? Slight difference. So you can see the discriminant, the distinguish 2 groups is not really easy. So if easy case, for example, we separate the lions from tigers with some maybe the weight or height or some other statistics, then probably the distribution is like this. So it's clearly different, but this case, it's really hard to distinguish it. So it's not really the easy. And I think that if we have multiple predictors, that we have LD2, LD3, and so on. I'm not exactly sure how many the linear discriminant function here. If we have the 5 predictors, possibly maybe we have 4 linear discriminant factors. Okay, so that's the thing. And the prediction works in the same way. So you have to prepare the estimated model and the new data set in the same structure as training set. Then actually the result include several objects. So actually the probabilities and also the binary, the predicted values, the down and up. So here 2 is up and 1 is down. So these observations are predicted as up. So actually the first 3, maybe 10 observations are all up. So if we pick up head, so head basically pick up the first 6 observations. You can specify options to make it 5 or 7. But OK, so first 6 observations are predicted as up. So yeah. Yeah. Yeah, but note that this is just a 1-day future prediction. So that means that this is for maybe January 9th, but we have to have the data from January 2nd to 6th to get this value. So we cannot predict the value for data up to 2004. We cannot. And using LDA, so this is the performance table. This is predicted, so this is predicted, and this is truth. So in total, we have the 141 correct predictions, and we have the 111 failure. So 35 plus 76 over the summation. So summation is 252 last time. So this is 111 over 252. So error rate is certainly smaller. Yeah, so sorry. So this is 1 minus error rate. 1 minus error rate. So 56% correct. So error rate is 44%. That is good for stock market prediction. Yeah, so it's known that the stock market can be predicted 60% correctly, but that does not mean you can make money, because if you have the very large movement, maybe stock market plunge, and we cannot predict it, then we make a huge loss. So the error rate does not indicate the performance of measure. Okay, so that is LDA. So do you have any questions so far? So LDA, much less information. So only descriptive statistics and the predicted values. So we don't have much statistical analysis here. We can only calculate probabilities and the predicted values and the linear discriminant function, and that's it. Yeah, so the next one is the quadratic discriminant analysis. So this is in the same package, the mass package, and the format is exactly the same. So, but just the QDA function. And the summary statistics are different, but almost the same. And I believe that we have also function to extract the variance covariance matrix. But here we just do the same thing as the linear discriminant analysis, the predict for the test data set and the make table. And actually we have 151 correct predictions and the 20 plus 81 errors. So only 101 errors out of 251. So error rate, again, this is 1 minus error rate, is almost 60%. So error rate is 40.1%. So that is pretty small. That's the interesting result. Yeah, so this is for the test performance. So test performance. So the QDA often suffers from the overfitting, but we don't have overfitting problem. Maybe just we are lucky or QDA is actually good. So this is for the test set. So it's not because of overfitting. We are just lucky or the QDA is really good. And nearest neighborhood method. So we even have less output for this method. So KNN is more prediction-oriented method. So less theory behind it and the more numerical more data-oriented method. And the KNN that we use the library class. So this is basically classification problem. So library class is used for KNN. And KNN function is used, but the format is a little different. So training set, at first the predictor for training set, then predictor for test set, and then the response for training set. So we have to have the 3 objects. So this is different format. So in the past, basically we have to regress the training set, the train Y tilde train X. So this is the format for logistic regression and LDA, QDA. And for the test performance, we have to use the predict function. Right? So that was the LDA and logistic regression. But here, we don't use this. And you have to just input these 3 objects. Then specify K. So this is the K nearest neighborhood. So just the K is equal to 1 means the only closest observation we use. K in K nearest neighborhood. K nearest neighborhood. So K is equal to 1 means the closest observation is chosen. So usually it overfits the situation. And actually the performance is here. Performance isn't really good. So we only have the 126 correct predictions and 126 wrong prediction. So yes, just the KNN function that makes prediction already. So only predicted values are extracted, not much more analysis. So only 50% correct. How about KNN with K is equal to 3? Then actually the 53.6% correct. So error rate is 1 minus 0.536, so 0.464. So yeah, it's reasonably well, but not as good as QDA. Yeah, so we cannot enter chapter 5 today, but this is how to run the logistic regression, LDA, QDA, and the nearest neighborhood. Do you have questions?